team, let's take a look at homework 11, where we talk about culverts and weirs, so hydraulic structures. First look at problem 8.5.2 in the book. The problem is we have a 13.1 foot wide rectangular channel. It's conveying 72.7 CFS. And we need to determine the depth of water that would be produced upstream of a weir that is 3.28 feet tall, built across the floor of the channel. Okay, so we're not getting any other information, so we're going to assume that it's an uncontracted weir. So this is what our weir would look like, uncontracted weir. The flow isn't contracted to go through the weir. And then determine the velocity of the flow over the weir. Assume weir friction loss and velocity head upstream are negligible. Okay. Well, what's the first thing we know about weirs? They cause critical depth to happen over them. So the first thing we work with is we know that critical depth is occurring over this weir, right there. So YC. And then maybe it slips down into supercritical flow as it goes over. And then if the slope stays the same, we'll get a hydraulic jump and then we'll go back to subcritical flow. Okay, so YC, let's calculate YC. Well, let's go to our YC equation. We've seen this a number of different ways, but look at Q squared over GB squared to the 1/3. This is based on the energy equation and taking the derivative of it and setting it to 0. So this is just a standard equation we use. We also have seen this form, Q squared over G to the 1/3. And just know that Q is equal to big Q over B. So this is unit discharge. This is discharge. Unit discharge is just discharge divided by the width of the channel. Okay. So step 1 is we need to find the flow depth over here at the weir. And then step 2 is we go back to the energy equation that we did for weirs and flow approaching weirs, and we're able to back calculate this discharge using this specific energy equation, which just states that E1, this is 0.1, this is 0.2, is equal to E2, which is also the critical depth, plus Z or P or whatever we're going to call this height right here. And the reason is if we have critical depth here, that's minimum energy. It's going to be less than this energy right here. So we have to account for the additional elevation given by this step. So let's calculate critical depth. And then we'll go use the energy equation to solve for E1 upstream, which we'll assume is equal to the depth. So critical depth equals YC 72.7 CFS squared all over 32.2 feet per second squared times 13.1 feet. And that's all squared. And then we'll raise this to the power of 1/3. That ends up equaling 0.985 feet. So that's our critical depth. We can calculate the velocity. Q is equal to, or sorry, V is equal to Q over the area of the flow. And the area of the flow is going to be the depth of the critical flow right here, and then the width of the channel. So 72.7 CFS divided by length, 13.1 feet, times the depth, 0.985 feet, divided, and we end up with 5.63 feet per second as our velocity. Now we can go back to our specific energy equation. This is equation 8.7 in your book. And we can say that H upstream, or E, we'll just call it E for the specific energy equation. E1 is going to equal to E2 plus, we'll call it Z, is the height of the weir. Sometimes your book refers to it as P, okay? It also says that in the problem that we'll assume there is no friction loss and that the velocity head upstream is negligible. So if the velocity head upstream is negligible, well, specific energy is equal to the depth plus v squared over 2g. This is the velocity head. We're saying that's negligible. So we're just saying that the specific energy is approximated by the flow depth. So then we'll say y1 for E1 is equal to E2, which happens to be EC. So critical energy over here, which happens to equal 3/2 YC. And that's, again, going back to specific energy and taking the derivative of it, setting it to 0, so we find the minimum energy. So for rectangular channels, the critical energy is equal to 1.5 or 3/2 times YC. That's for E2, and then Z we're given as 3.28 feet. So now we can solve Y1 is equal to 3/2 for critical depth. And there we go. That's our depth upstream. So what we did is we just used the assumption of no energy loss over the weir. We knew, because this is what weirs do, that we had critical depth here at the weir. And then because the problem said, let's assume no energy loss and that there's no velocity head over here. Well, now we can calculate our flow depth and our energy over here. We relate it to the energy over here. So this is a big key part of solving this problem, is understanding that E1 upstream of the weir is going to be equal to E2 at the weir plus Z, and then E2 is equal to our critical energy at the weir. Because we're at critical depth, that means our energy is critical energy. The next problem, 9.4.7, is another weir problem. Here we have a 90-degree V-notch weir, standard USBR. It's measuring a flow rate of 0.295 cubic meters per second. And we're supposed to determine the length of the contracted horizontal weir, again, USBR, that would produce the same head or H upstream of this weir at that given discharge. Let's take a look at these weirs, just so we know what we're talking about. So here we have our 90-degree V-notch weir, standard USBR, given these kind of specifications. And here we have a contracted horizontal weir. Again, standard USBR has to follow these dimensions. These are the weir equations associated with those weirs. So here's the one for the V-notch weir. And then that's the 90-degree V-notch one. And then we have a rectangular one in there somewhere. This is the trapezoidal weir. Okay. Well, we'll figure it out as we go. So first we'll start with equation 9.14 for British gravitational units. And that says Q is equal to 2.49 H to the 2.48. So we need to convert to CFS, because that's Bureau of Reclamation works in CFS. So we'll do Q is equal to 0.295 cubic meters per second. And then that's times 35.1 CFS per cubic meters per second. And then we end up with 10.4 CFS. All right, let's plug that in and see what we get for H. So we actually just need to solve for H here, right? So let's just solve for H first. So we have Q over 2.49 is equal to H to the 2.48. and then we'll solve for H. H is equal to Q over 2.49 to the 1 over 2.48. All right. If we plug in our Q, 10.4 CFS 2.49, 1 over 2.48, we get H is equal to 1.78 feet or 0.584 meters. Okay, now the standard USBR equation was actually equation 9.2. So let's see, equation 9.12. And this is for the contracted horizontal weir. And that says that we have Q is equal to 1.84 times the length of that contracted weir, 0.2 H, H to the 3 halves. This is our weir equation. This is what the weir looks like. And this is our L. Okay. So now we've got a discharge rate. Basically, we just need to, and we've got an H, right? We solve for H. So we plug in our discharge rate, we plug in our H, and we solve for L. So that's all we have to do here. So we say, okay, we basically want to swap out a V-notch weir with a certain H and get that same H with a horizontal weir. It's the same H across these two. So we have to solve for L. We solve for H. All right, so we'll put in, again, this is equation 9.1.2, and this is SI units, so we just got to keep track of which units we're using. So 0.295 cubic meters per second equal to 1.84 L minus 0.2 H, which was 0.584 meters, and then 0.584 to 3 halves. Okay, so we'll rearrange, we'll solve for L, and we end up with L is equal to 0.476 meters. So that's the L we need to get the same H for the same discharge. So the next problem, 8.9.1, is a culvert problem. We're given the same culvert setup from example 8.5 in the book that we went over in class as well. We're given a diameter of 1.5 meters. That's what we saw. That's what we figured out that we needed based on the flow conditions. So now the question is, well, can we do something to this culvert design to reduce the required diameter? Can we reduce it, say, to 1.25 meters and save some money? Because, you know, pipes are expensive. Okay. Well, let's look at 2 ways we could do this. One, we could reduce the K entrance value. So use a well-rounded entrance. And then we could also increase the slope to 1%. So that might be one way to do it. Another is, could we replace the corrugated metal pipe to a concrete pipe, which reduces the N value, the Manning's roughness value. All right, let's look at the first example where we're gonna just change the slope and entrance conditions. Now, because we're using a culvert that has tight V flow. From the example, we found out that it has tight V flow, so it's submerged upstream, full pipe flow through. Then the way to calculate the energy loss in this is using a few things. We can kind of do this directly. So let's look at this. Let's just draw our culvert out. Okay, so we had submerged upstream, and then we had full pipe flow downstream. So we can say that head loss is going to be equal to this upper depth plus the length of our culverts times the slope of the culvert. So that's the kind of delta Z basically that we get. So length times slope is going to give us delta Z minus the diameter of our culvert. We can just rearrange this and say, well, if we just run the energy equation, we can say Y upper is going to be equal to the delta Z, which is L, or sorry, we should say minus L times S naught. Okay, so we go down there, we did this change in elevation. That should equal D plus head loss, right? We have our energy up here. We're assuming there's no velocity head. So we have our energy up here, and then we drop from here to here. We're dropping just that delta Z from the bed slope, right? We've got the diameter, so that's going to be the delta between these two, the top of the water surface. And then we have some head loss. So this is basically just an energy balance equation between the two. So we're just rearranging and solving for head loss up here, okay? So we actually directly solve the head loss using this equation. So head loss is equal to our upper depth, which we found from before as 3.2 feet plus our slope. In this case, we're increasing the slope to 0.01, 0.01 times our length, which happened to be 40 feet in the previous example. Sorry, these are meters. And then the diameter, in this case, 1.25 meters that we're adding the diameter in. So what would the actual head loss be in this case? 2.35 meters. And that's literally just saying, well, we had, from before, we figured out that we had a submerged flow up here. The flow moves through the culvert, it drops by the length times the slope, and then whatever energy is available is going to be related to that diameter of the pipe. So the Y is equal to the diameter, right? Okay, then we can look at equation 8.18, and we're going to change our K entrance to 0.2 this time. Before it was higher. Before our K entrance was 0.5. So we reduced it by a little bit. And then we'll write out the energy equation for that. So head loss is going to be equal to K entrance for the well-rounded plus the energy loss from the Manning's equation. That's N squared L over the hydraulic radius. So the 4/3 times 2G. And then plus our exit loss. And all of that is times V squared over 2G, but because we're using discharge, it's going to be 8Q squared over pi squared G d to the 4th. So we'll plug in our numbers. We'll add 1, we'll add 0.2 together, so that's 1.2 plus Manning's roughness, so that is equal to 0.024 for corrugated metal pipes, and that is from table bear with me. Table 6.2, corrugated metal pipe, 0.024, concrete pipe, 0.013. Okay, 0.024 squared times 40 meters all over a hydraulic radius. So we know it's a full pipe, so that's going to be D over 4. R is equal to D over 4 for a full pipe for a circle. So 1.25 meters over 4. So the 4/3 times 2 times 9.81 meters per second squared. Times 8 times our discharge, which was 5.25 cubic meters per second squared all over 3.14 squared, 9.81 meters per second squared times 1.25 meters to the 4th. So that's D to the 4th, D to the 4th. All right, so we plug all those numbers in, we get head loss is equal to 3.10 meters. Okay, now let's compare that with what our head loss should be if this smaller diameter pipe would work. So this is a greater head loss than 2.35 meters. And what we calculated up here is the head loss that you could have such that you're able to maintain the depth up here and have everything be not submerged down here. If you have more than that head loss, then basically it's gonna be harder to push that flow through. You're gonna get a higher backwater up here. So what we're saying is the actual head loss in this pipe is 3.1 meters, given all these things that we calculated here. Whereas the total tolerable head loss, just doing the basic energy equation between these 2 points, could be 2.35 meters. Otherwise, you would need a bigger, you'll get a higher backwater under this equation, under this situation. So for A, it's not going to work. This 1.25 meter diameter is not going to work by just changing this coefficient and increasing the slope. So let's look at the next example, and that's changing the pipe material to concrete. I'll go to the next page. So N for concrete is equal to 0.013, and then the slope isn't changing. So the slope from before was 0.003. Okay, so now we'll do the same thing where we do the energy equation. We'll compare it upstream and downstream and find our maximum allowable head loss, and then we'll actually calculate the head loss and compare. So head loss is equal to the upper depth plus the slope times the length minus the diameter. Okay, so that depth we said from upstream was 3.2 meters. That slope, and then minus 1.25. So we're going to say, can we use this diameter of 1.25 meters? All right. So in this case, the head loss is equal to 0, so 2.07. Okay, so now we calculate the actual head loss and compare. So as before, our head loss is equal to KE N squared times L R to the 2/3, sorry, 4/3, to G plus our exit loss times 8Q squared all over pi squared G d to the 4th. All right, so if we plug in all these values, we're going to use 0.5 here, same length, and we're going to use 0.013, so that's going to change it. Hydraulic radius will be the same because the pipe's flowing full. Q is going to be the same. Diameter is going to be 1.25 meters. So head loss will end up being 1.98 meters, which is less than 2.07 meters. So we're okay. And what that means is the actual head loss in this system with this diameter pipe and this roughness, this length, results in this head loss. And because it's less than the maximum head loss we can tolerate with this given backwater upstream, what that means is we can use this diameter with that smoother pipe and this backwater. If this were greater than the maximum allowable head loss, then we would end up with a greater backwater. So Y would have to increase so that this head loss would end up decreasing, or would end up meeting the true friction head loss in the pipe. The last question, 8.9.4, we have a culvert that it's a 2x2 box culvert, 2x2 meters. And they give us a bunch of information, square edge entrance, so that's our K entrance, the slope, the length. They say that the headwater elevation has to be less than 3 meters to avoid flooding of our homes upstream. So there's a house sitting here at this elevation, and we want to make sure that we keep underneath that elevation from the backwater that would occur at the 100-year flood event, or the 1% annual chance flood event, such that, which is 12.5 cubic meters per second. We're told that it's a concrete box culvert, and we're told that given the channel dimensions downstream and that flow rate, you do like a HEC-RAS model, a backwater model, and you'll end up with a flow depth of 2.75 meters above the invert or bottom of that culvert. So the question is, what is the headwater elevation? Is it less than 3 meters? Will we flood homes? Okay, well, so we have, just by setting this problem up, we're told that the tailwater elevation is 2.75 meters. That's greater than the top depth of the box culvert. So we know that we're gonna be submerged downstream, and we know that we're probably gonna be submerged upstream simply because we have to be somewhere less than 3 meters. So this puts us in a class A type of flow setting. And for class A flow, we can use equation 8.18 to calculate head loss. So the way this problem works is we need to calculate our head loss and then use the energy equation to calculate what the actual headwater elevation is. So we'll use equation 8.18 to calculate head loss, and then we'll use the energy equation, which says the headwater elevation, or Y upper, plus this delta Z, which is going to be slope times length, right? Should be equal to the tailwater elevation plus head loss. So once we calculate head loss, we know the tailwater elevation, we know the slope and the length, we can calculate the headwater elevation and basically work our way back up to that using the energy equation. All right, so head loss is equal to our K entrance plus N squared L over R to the 4/3 times 2G plus our exit loss, which is 1. It's always 1 in these problems. And then times the v squared over 2g, which is just q, it ends up being q squared all over 2g a squared. Because we're doing it with a rectangle, we can calculate this area more directly. Okay, so hydraulic radius is equal to the area over the weighted perimeter. This is pretty easy to calculate. We just have the area, which is 2 by 2, so 4 meters squared. The weighted perimeter is going to be simply the perimeter of that box culvert, which will be 8 meters. And so we end up with 0.5 meters for hydraulic radius. Now we can plug all our numbers in. Head loss should end up equaling 0.81 meters. Nothing fancy to do there. Our Q is 12.5 cubic meters per second. Our area is 2 times 2. Just calculated that. Our Manning's is 0.013 for concrete. And then we're given our length, and our K entrance should be 0.5 because it's a square entrance. Okay. So we've calculated head loss. Now we just go back to our energy equation and we say headwater elevation. We'll just bring slope over on this side times length. So that should equal to the tailwater elevation plus our head loss minus the slope times the length. So that delta Z. All right. So headwater elevation is equal to 2.75 meters. Plus 0.81 meters for our head loss, minus the slope, which is 0.02 times the length, 15 meters, and we end up with 3.26 meters. So yes, we get flooding. Maybe we want a bigger culvert. The velocity in that culvert, another part of this, I'll let you calculate that, but that's equal to 3.13 meters per second.